In solving polynomial equations, you came across situations in which there were no solutions, or not enough solutions to match the degree of the polynomial. If you recall, the lack of solutions, or an insufficient number, is indicated by a polynomial graph not crossing the x-axis, or not crossing it enough times. In this video we'll be looking at these cases to find polynomial solutions that are complex numbers. We'll focus our attention on quadratics and cubics. Let's start with a quadratic equation with no solutions. This is a parabola that doesn't intersect the x-axis, so it has no solution. We can confirm this by calculating the discriminant. With the discriminant less than 0, that confirms there are no solutions. But we need to amend what we said before. The discriminant determines if there are solutions that are real numbers. There are actually two solutions to this quadratic equation, and we can use the quadratic formula to find them. Plugging in the values into the quadratic formula, we end up with the expression the square root of -1. This value was replaced by the symbol I. The square root of -1 is not a real number. It is known as an imaginary number, and it is part of the complex number system. In fact, real numbers are also a subset of the complex number system. Complex numbers are two-dimensional numbers written in the form a plus bi, where a is the real number part and bi is the imaginary number part. Because they are two-dimensional numbers, a two-dimensional coordinate system is needed to graph these numbers. The horizontal axis is for graphing the real part and the vertical axis is for graphing the imaginary part. As you can see, this is why this number system is called the complex number system. Compared to the real number system, there is a lot more going on with these types of numbers. Going back to the quadratic that we solved, the solutions are 1 plus I and 1 minus I. This is the graph of these solutions. Notice how they are symmetric across the real axis. These solutions are called complex conjugates. In general, complex conjugates form a pair of complex solutions. This is important for our study of polynomial equations. Complex roots come in pairs, as conjugates. There won't be a polynomial solution that is a single complex number. Now we can get a much clearer picture about solutions to quadratic equations. In the case where there are 0 real solutions, there are 2 complex solutions. In the case where there is 1 root, it is based on a squared binomial, so technically that is 2 roots, called a double root, even though it's the same number. Finally, there is the case where a quadratic has 2 real solutions. In all 3 of these cases, a polynomial of degree 2 has 2 solutions. Make a note of this. Now let's look at cubic equations. Previously you saw that a cubic equation can have 1, 2, or 3 solutions, depending on the number of times the graph intersects the x-axis. Remember that every cubic has at least 1 linear root. Now that we've introduced the concept of complex solutions, let's revisit each scenario. The cubic equation with 1 solution has a linear root and a quadratic root that has no real solutions, as you can see from this parabolic part of the graph, which doesn't intersect the x-axis. But now we know that this type of quadratic has complex roots. Use the quadratic formula to find those roots. The cubic can be factored as the product of a linear binomial and a quadratic. We know the quadratic doesn't have real solutions. Using the quadratic formula we find the 2 complex solutions. The result is that this type of cubic has 3 solutions, 1 real and 2 complex. This is the only case in which a cubic can have complex solutions. This screen summarizes the 3 possibilities. In all 3 of these cases, a polynomial of degree 3 has 3 solutions. Are you seeing a pattern? Let's look at an example of using complex roots. Here is a parabola. It has real roots and represents someone kicking a football from the origin and having it land at x equals 20. The equation for this parabola is shown. But suppose midway through its flight, the football is sucked into another dimension, of the upside-down world and follows a different parabolic path. Where will the football land in the upside-down world? Here is the equation of the path of the football in the upside-down world. It's part of a parabola with no real roots. So how do we find out where it lands? Use the quadratic formula to find the complex roots. As you can see, the coordinates of where the ball lands are complex numbers. Complex number solutions result in numbers that are two-dimensional. With quadratic equations, these solutions occur when the polynomial graph doesn't intersect the x-axis, and in the case of cubic equations, when they only intersect the x-axis once.